All right, so 4.3 is how the derivative affects the shape of the graph. Honestly, we've been looking at how the derivative affects the shape of the graph since the beginning of chapter 3. This is truly when that chart I gave you really comes into play. So if you've yet to memorize my chart, I would highly suggest memorizing it for this section, because everything about that chart helps us understand extrema. So we talked about the extreme value theorem, we talked about the mean value theorem, and we talked about this theorem. Well, the extreme value theorem said that if you had a closed interval and it was continuous, then you were guaranteed an absolute max and an absolute min. The first derivative test for extrema is a extension or moderation of that that's going to help us be able to graph. So we already know how to determine relative extrema. We get relative extrema by setting the derivative equal to 0 or finding where it does not exist. Those are known as the critical points. The behavior of the first derivative before and after those critical points will now help us determine whether these are maxes or mins. So if something is increasing and then decreasing, you know you have a relative max. If it is decreasing, then increasing, we know we have a relative min. In terms of our derivative, if it's increasing on the original, our derivative will be positive. If it's decreasing on the original, our derivative will be negative. So we're looking for this positive, negative, increase, decrease behavior around those zeros. Okay, so given the graph of f below, label the relative extrema. So when we look at that graph, I would say that we have approximately a relative max occurring at y equals 3, when f is 1.2, and we have a relative min occurring at like negative 3.1, when f is probably about 4.8. And again, you're estimating, so if you're 4.75 or 4.9, those are all perfectly fine. So what I want you to do now on that second graph is go ahead and sketch the derivative of f as accurately as possible. So recall that when we're talking about our derivatives from our originals, if the original graph is increasing, then our derivative needs to be positive. If our original graph is decreasing, our derivative needs to be negative. And if we have an extrema, our derivative needs to be 0. If we're talking concavity, if the original graph is concave down versus concave up, then this graph is increasing or decreasing, and our point of inflections will be our new extrema. So if I'm looking at this graph here, I'm probably going to say that we have a point of inflection about 1, 2, 3, probably at f of 3.2. So that helps me when graphing my next graph, because that tells me I need to have either a max or a min at 3.2. In this case, if it goes from concave down to concave up, we're going from decreasing to increasing. So if it's decreasing then increasing, that makes 3.2 on its derivative a min. So hopefully your graph looked relatively something like this. Here's my min at 3.2. Here's my zeros at 2 and 4.8. Or 1.2 rather, sorry. So you can also see that the original was probably cubic and the derivative is now quadratic, which means the second derivative would be linear. Okay? Questions at all? Pretty easy, right? Everything kind of makes sense. We've talked a lot about that. Okay? The first derivative test, honestly, is a fancy way of saying if and only if the derivative changes from positive to negative at a critical point C, can F have a local max at C?
10 minutes, wait, 10% of it.
Maybe after. If F prime changes from negative to positive at C, then you have a local min. And if F prime does not change sign at C, then you do not have either a min or a max. So that's one of those things that they set you up for those tricks. There'll be questions where you'll find a critical point, but that critical point might have a positive to the left and a positive to the right. Therefore, that critical point is not a relative max or min. It's like one of those blips on the graph that look like this. You know what I'm talking about? Like if you see a graph and it has the little hump in there, but it's not considered a critical point, that would be because this would stay decreasing, right? So the derivative would stay negative, even though you have this critical point occurring. All right, important. If you are asked to find an absolute max versus just a max of a function on a closed interval, you must test the endpoints. What theorem is that? If I have to test the endpoints, what theorem is that? No. No. Yes. Think extrema EBT. Endpoints extrema EBT. Because extreme values are extrema, and you're checking the endpoints. So again, this statement right here is coming from EBT. Okay, so that leads us into looking at examples. Now, this is where I have a love-hate relationship with the AP test. So we're given the function f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. And it says find where the graph increases and decreases. So we teach you to find the derivative. So that's always step one. I said no, this
Really? Not really sweet.
This is small. Okay. What would you do to this function to make it easier to find the zeros of it?
12x.
Exactly. Take out your GCF. So now, in order to find those critical numbers, we set the derivative equal to 0. So again, my critical points come from setting the derivative equal to 0. So we're going to get x equals 0 over here. Does x squared minus x minus 2 factor?
Yes.
Yes, it factors very nicely, so you don't need quadratic formula. You get x minus 2, x plus 1, which gives x equals 2, and x equals negative 1. So we're super excited. We have 3 critical points. That should make sense. If the original was a 4th root, that means it's even, so it's going up in opposite directions. So that means it has 3 relative max and mins occurring. What we have to do is determine increase or decrease. So the easiest thing to do is to set up a sign chart. This is where I said the love-hate relationship. The AP test readers will not look at or grade your sign chart at all. You have to put into words the increase or decrease intervals. So this is awesome. It helps you. You get these values, but they mean nothing to a reader. So what we have to do is put our 3 critical points on the number line, and then you have to remember that this number line you're looking at is with respect to f prime. So what I do is I say, okay, I want to find what is happening on the derivative around these critical points. So I want to know what's happening at 1, what's happening at like negative a half, negative 2, and 3. So typically it's easiest to plug in to our factored form because all I need to know is the sign. So if I start with 3, if you plug 3 in here, you're going to have positive or a negative? A positive. So that's all I need to know. If I plug 3 in here, am I going to get a positive or a negative? Positive times positive stays up. Okay, we're good. If I plug 3 in here, positive or negative? So positive times positive is a, therefore the derivative is positive greater than 2. I don't need to know what the value is, I just need to know the sign. Plug in something between 0 and 2, such as 1. 12 times 1 is positive. 1 minus 2 is, so positive times a negative is a, okay, so we got a negative. 1 plus 1 is 2, that's positive. A negative times a positive is going to give me a negative. Okay? Yeah, plug in negative 0.5. Once again, I don't care that negative 0.5 times 12 is negative 6. I just care that it's negative. So I get a negative, and a negative is going to be a negative. And then that makes this positive, though. Negative times negative is a positive. And here, a negative plus a number that's bigger than that negative will be positive. So I get a positive value out of that whole thing. Okay, plug in negative 2. That makes this negative. That makes this negative. That makes this negative. 3 negatives stay negative. So, I have all this information now about the derivative. Well, if you go back to that chart I told you is your best friend, if the derivative is negative, the original function is doing what? So I draw a little decreasing line down to my critical point. If the original function, or if the derivative is positive, the original function is negative. is kind of V-ish. Do you see the quartic function? Can you see that W shape that we know a quartic's going to give us? It's even, so it's got to end in the same direction. That makes -1 and 2 mins and 0 a max. So I said my love-hate relationship comes into play. This right here means absolutely nothing on your AP test. You have to put that into words. You have to know what that is saying. So where we have to go next is to say that F is increasing from -1 to 0 and 2 to infinity. So F is increasing from -1 to 0 and 2 to infinity, and decreasing from -infinity to -1 and 0 to 2. Okay, I believe it also asks you for the max and the mins, right? So mine's like on my next page, which is going to be a pain. So let me see if I screenshotted it. We good on this one? All right, so what we're going to do. So, let's go back to talking about the original. And we kind of already talked about this. I hinted and I said, hey, what's that showing you? Well, it's showing you that you would have a local max at 0. Don't fall for the trap. Where do I plug that 0 back in? To the original. So it's going to be 0, 5. So if you want to know the exact point, you plug this x value back into the original. How do I know this is not an absolute max? Unless I have a closed interval, right? This is going to be increasing indefinitely. Okay, and then we would have a local min in 2 spots, at -1 and at 2. So if you plug in -1, you should get 0. And if you plug in +2, you get -27. This would then probably be my absolute max. I mean absolute min rather, because it is the lowest point on that graph. And next. Okay, given f of x equals x squared root 4 minus x squared, find where the graph increases, decreases, and has your local max and min. The process for this is always going to be the same. Find your derivative, find your critical points, get yourself a sign chart, and then you can answer any question you want. So, f prime of x is the first times derivative of the second. Don't forget that when we take the derivative of the square root of 4 minus x squared, that we have to take into account the derivative of the inside, which is -2x. So first times derivative of the second plus the second times the root of the first. So here, the 1/2 and the 2 cancel. You get negative x times x, so you get negative x squared over the square root of 4 minus x squared. Here's what I would do. This square root isn't in the denominator, right? But if I multiply by this denominator, I can get them to have like bases and get rid of my square root, right? So what I would do is I would actually multiply this by top and bottom of the square root of 4 minus x squared, thus creating a like denominator and turning this numerator into positive 4 minus x squared without your square root. Because look what happens. It's so much easier to look at 4 minus 2x squared and this for critical points.
How did you do that? Yeah.
So if you, this needs this for the denominator.
Right.
So I multiplied by the square root of 4 minus x squared, square root of 4 minus x squared. Square root of 4 times square root of 4 is 4. Square root of 2 times square root of 2 is 2. So if you multiply like square roots together, the square root goes away. So it also created that common denominator. So now to find your critical points, you just set this numerator and that denominator equal to 0. Yeah?
So it only gets rid of the radical sign on the top.
Correct. Because there's nothing on the bottom. Like, it's like the opposite of rationalizing your denominator. I rationalized my numerator.
Oh, it's just like what happens to that? What happens to the 4 minus x squared to the negative 1 over 2? So wouldn't that be on the bottom? And then once you
To
multiply
the negative
it
1
would,
over 2, that's over here.
yeah, and then once you multiply it by whatever that is, it would cancel it out, right?
No, you're
This
not
is, so this
Oh, okay.
piece is different from what I just multiplied.
Oh, okay.
Do you see the plus sign in between them?
Yep.
Yeah. I did it to make them like term, or to make them have a like denominator. Okay, so there we would set 0 equal to 4 minus 2x squared and 0 equal to the square root of 4 minus x squared. So these are going to give you the f primes of zeros. These are going to give you the f primes of dne. So you add your 2x squared over, divide by 4. No, just divide by 2. I said divide by 4. I meant divide by 2. So again, I added the 2x squared over, or the 4, whatever way you want to go, and then divided by the 2. So we're going to get x equals plus or minus root 2. What do we know about over here? You would get rid of the square root by squaring both sides. So then you get 0 equals 4 minus x squared. So then you get 4 equals x squared. So x equals plus or minus 2. Positive and negative 2 are in my original domain because that's not in the denominator. So we don't have to worry about that. Okay, what we do need to know is where do these values sort of fit on a number line? Is the square root of 2 going to be bigger or smaller than 2? Smaller. So we know that positive root 2 is somewhere in here and negative root 2 is somewhere in there. We would also know that the square root of 1 would be in between here. The square root of 1 would be smaller than the square root of 2. So 1 is valid values to plug in for this. So plug in 1 to your derivative, which is Right over here. 4 minus 2 is going to be positive. 4 minus 1 is 3. Square root of 3 is going to be positive. So this right here is positive. If you square a negative 1, is it going to change any of these values? So that means that this right here is also positive. Okay, can I plug in anything bigger than 2 or negative 2? What happens if you plug in 3 to this denominator? Yeah, because you're going to get 4 minus 9, so you can't take the derivative of a negative. So this does not live in our domain. And that would actually happen up here too, right? Because the square root still matters. So the domain of this function is actually negative 2 to 2. And sometimes we end up seeing that as we work through the problem. What would be between negative 2 and root 2? Anybody know what root 2 is? You should, because it's kind of like a tricky one. Okay. So wouldn't it be, no, you're fine. So 1.4 is a fair thing to say. Would it be safe to put in like 1.9s then? Like you want to just know something that's safe to plug in. So I would say it's definitely safe to plug in like 1.9s. And again, you're going to get the same value on either side because it's squared. So 1.9 squared is pretty close to 2, right? But it's less. So 4 minus 2 times 2 is 4. If you take 2 times anything a little smaller than 2, it's going to be bigger or smaller than 4. Still smaller, right? So your numerator is going to stay positive. So what we have to do is kind of look at it and say, okay, where are we positive? Where are we negative? So okay. So from negative 2 to negative root 2, we should be negative, and from root 2 to 2, we will also be negative. And then from there, you would just say increase, negative root 2. This is where you got to be careful. To root 2. I wouldn't include 0 because we don't know what's quite happening at 0. And decrease. You can have it as a bracket or parenthesis because it's an endpoint. They would accept either.
How do you know that's negative from the square root of 2?
Because that's going to give you a negative value.
One in like 1.8 or 1.9.
And then you know your denominator is always positive. So negative to that positive is okay. Okay. So again, that makes this go decrease, increase, increase, then decrease. I did my decrease too soon. Yeah. Then decrease. So we have a min at negative root 2. And a max at positive root 2. Nothing at 0 again. So that's why I said critical points don't have to be extra. Critical points don't have to be extra. So all the way for Friday, because I want nothing tomorrow from any of you, we're doing page 215, 1 to 6, and 21. That's it. 215, 1 to 6, and 21.